what we're going to be going over here is a quadratic function, and really it's going to be like an ellipsoid here. And with this quadratic function, we're going to be calculating the eigenvectors and the eigenvalues. And when we calculate these eigenvectors, it really causes a rotation here in our ellipsoid here. So what we're going to start with is this quadratic function here for the ellipsoid. You're going to have some coefficients here, 103 times some x squared term plus 125 here, coefficient times y squared, and 66 times z squared. Okay, so that's what we're working with here. But along with that here, we're going to have some cross terms between yz, xz, and xy, and each of those has a coefficient here. And then we just have this lone value here, 294. But when we calculate our eigenvectors and values here for this quadratic function, we're going to really come up with a function that looks like this, where the cross products are going to be eliminated essentially. And we're going to look at how we do that. So instead of having 103x squared, we're going to have 147x squared. Instead of y squared 125, we're going to go 98 for y squared, and then z squared is going from 66 to 49 c squared. So what we want to do is we want to look at how we'd come up with this, really looking at it here where we're going to be eliminating those cross terms here. And we do that here because it makes it easier. Well, that's how the eigenvalues really are for this function here. Okay, so looking at it pictorially here, so if we look at it with the cross terms, you're going to see we got this ellipsoid here. I did put a hole in it here to get an idea where our axes are going here, the x, y, z axis. So you can see they're canted off, and this ellipsoid here is sort of at an angle here. And if we go down here and just looking at it, rotating at 90 degrees, you can see the same thing. Your axes here are canted off, but they're really following this ellipsoid here. It's really, the axes are really symmetric to the ellipsoid here, but it is in fact canted off at an angle. So what we're going to do here, when we moving over here looking at the top here, so we're going to take and we're going to calculate the eigenvectors and values for this function that we're looking at. And really by doing that, those eigenvectors or eigenvectors and values really straighten out this function where it becomes really a perpendicular function here when you got the x, y, and z-axis. So you can see it's, again, very symmetric, but we've straightened out the axis compared to the form here where we got those cross products. And those eigenvalues are really represented by the x, y, and z axis here. I'm showing it in blue, red, and green here. And if we go down here and look at it over here, you can see the same thing, looking at it into it here. Okay, very perpendicular, very symmetric here. And moving over here, you can see how it's canted off here. But we are going to go through and we're going to do an algebraic solution to determine these eigenvectors and values here. And then if we move down here just to get an idea here, looking at over here, eigenvectors, this is where those eigenvectors, their unit amount is going to be less than a unit of 1 for each of those axes. And then for the problem I'm looking at here, those eigenvectors, really the red and the blue one here are represented by that eigenplane, and they're 90 degrees apart, and along with they're also 90 degrees to our green eigenvector here. And these eigenvectors really control the direction. But the point is here, these eigenvectors here with our regular polynomial here, quadratic function, before we straighten it out, you can see they're always less than a unit of 1. They'd be like 0.5, 0.6, 0.7, so forth. Okay, so what we're going to do here, when we moving over here, let's look at our eigenvectors over here. Now, what we do essentially here, you can see it. I'm just showing a rotation. I'm just showing we're going to rotate. This green ones are going to rotate up here. Red and blue are going to rotate as well. But they're still going to maintain their reference here at 90 degrees apart for each of them. But what's happening here, I just calculated out the degrees of rotation. X, it's going to go in 73 degrees in X, Y, 64 degrees, and Z, 31 degrees. So you can see we got our axis of rotation here in 3 different axes. And when we do that, our eigenvectors are going to actually equal 1 after we do this rotation. So when we multiply our eigenvectors times our eigenvalues, we're always going to use a multiple of a unit of 1. Whereas with our skewed term here with the cross terms in it, our eigenvectors here are less than a unit of 1. Okay, so that's what we're going to do here pictorially. So let's go and let's do start with our calculations. Okay, the key to this whole thing here, and let's look at it. We set up a symmetric or square matrix here for this ellipsoid here. So we started with our function here, and we're working off this function that we started with here. So what you have to do is a square matrix. So you got to set up a diagonal here, and you've got an upper triangular, lower triangular, and you're dividing up or you're balancing these terms here, the cross function terms here. The squared terms are going to follow the diagonal here. So what you're going to do here for your matrix, you're going to set up on your these x, y, z, and then unit of 1 here. Those represent our columns. And then alongside our side here, we got our rows, x, y, z, and 1. So it's really easy to do this here when you set it up in this way, looking at coming up with this algebraic solution to our problem. So we start out with our x squared, 103, so that would be x column times the x row, 103. Okay, so that's your squared term. Y squared term, same thing. You got what? Y column, 125, y row, 125. So that's y squared, 125. And then if we move down here to z squared, what is that? Okay, we got our z column here, 66, z row, 66. So that gives us a z squared term. So you see what's going on here. You take your row times your column, and you get whatever that is. So x times x is x squared, y times y is a y squared, z times z is z squared. But the key is for these other ones, you have to divide everything by 2 here. So if we look at our yz function here, a minus 60, let's look at that. So that's going to give us here on our upper triangle, we're going to have y, half of minus 60 is minus 30. And then that's in our z column here. So that's our yz here. Z times y, half of it, minus 30. And then if we move over here to our 12, minus 12, or xz, what is that? Column or row x here. And it's half of that. So that would be minus 6. And then z is your column here. And then maybe you didn't look at it. I should have looked at it looking at our mirrored angles here. So let's look at, maybe let's look at this one. Minus 6 here. So the mirror part, or flipping it over here, is going to be a minus 6 here. So that would be what? xz. xz, half of that, minus 6. And then for our 30 was the same thing here if I didn't go over that. So we had our 30 here, y, z minus 30. Then the one over here would be y, z, or it would be, what is it? y, z, and then z, y, essentially. Just understand that. You just have to come up with, make sure you get your rows and columns here multiplied out properly and divided up. And then we had this 48 here. What was that? That would go over here. So that's 48 is xy. So you got a y here, x, half of it's minus 24. The other part goes over into the lower triangular here, y, x, minus 24. Okay, and then we just have this lone factor here, minus 294. That's why I've set up this column here, 1. And 1 row, column 1. That goes right in the bottom here, 294. And that does sit on the triangle, or sits on the diagonal, excuse me. So you understand how to set that up. Then you have to have identity matrix here when we're solving this problem. I got a 4x4 matrix with 1s across the diagonal. Okay, so just using some computer algebra system. In this case, I'm using MapleSoft for all this. So what you're going to do is you're going to take this matrix, square matrix that you set up, and then you subtract from it, and you add in this lambda. It can be any variable, but they generally use lambda times the identity matrix here, 4x4. So what you're going to do is you can see this matrix up here, our symmetric square matrix here. We just added in that lambda, and essentially what you're doing is just subtracting lambda from each of the diagonal terms here. Okay. And then what you would do here you'd call it out in this case for MapleSoft software, it's a determinant of this particular matrix, set it equal to 0. And then you're going to get some, I call it a polynomial here with one unknown, but it's got some terms here, like the solution here of that determinant would be some factored amount here, 10 to the 8th here. And then you're going to get some coefficient here times lambda squared plus another coefficient here times lambda plus lambda to the 4th, and this create all equal to 0. So you're just going to put up a factor that out, and you're going to come up really with your eigenvalues here. Lambda plus 294, lambda minus 49, lambda minus 98, lambda minus 147, all equal to 0. just solve that. Essentially all you're doing is setting everything, bringing those out. So your landed terms are just coming out to, these are your eigenvalues, minus 294, 147, 98, and 49. And then you'd also call out in your computer algebra system, call out for your eigenvectors here. You're going to have call out for eigenvectors. So for each one of these values here, you're going to get some eigenvectors shown in columns here. X, Y, Z, and 1. Okay, so now let's go on and let's look at this a little further. Okay, now that we've defined our eigenvalues here and our eigenvectors, and just so you understand, for each of these eigenvalues here, we have a group of eigenvectors here for the X, Y, Z, and 1 coordinates here. So each of our eigenvalues have a set of coordinates here as eigenvectors. Okay, so what we're going to do here is we first have to set up an eigenvector matrix. We're just taking these eigenvectors here and putting it in matrix form here. Okay, so what you're going to do here, and this is where you're going to set up the new axis, basis, null space, or kernel, whatever you want to refer to it as here. So what you do for your eigenvector matrix, for your columns here across the top, you have just put in some variable. I'm going to call them T1, T2, and T3 and T4. Those represent our columns, and across our side here would be our rows here, and let's define those as X, Y, Z, and also that 1 here. Okay, so with the computer software package, you just want to evaluate this to understand what's going on. You just take that P, your matrix here, whatever you have here for your eigenvectors here, times those variables here, T1 through T4 here. And what's going to happen? This is what's really happening. You're going to make a transpose here. This X, your X value that you're working with in our quadratic becomes this first row. So let's look at it. So X here equals these are all decimal points, 0.429 here times T2 plus 0.857 here times T3, and then minus 286 here times T4. And same thing for Y. Y row here just becomes this entire row here. So Y becomes 0.857 here, minus 0.857 here times T2, plus 0.286 here times T3, minus 429 here times T4. And same for Z. Let's just go through it. Z here is equal to 0.286 here times T2, minus 0.429 here times T3, and then minus 0.857 here times T4. So you guys see what's going on. We're just matching up our variables across here at top, T1 through T4, with our X, Y, and Z axes here. Okay, so now we have our X, Y, and Z defined here in terms of our variable, our eigenvectors here, T1 through T4. I left T1 out here, which really, there is a T1 value of 1 here, but I left it out. Okay, so what we're going to do here, just set up our new eigenvector basis. So we start with our quadratic function here, the original one that we have here with the X, Y, and Z, and then those cross terms here. What you do here is just using your software that you have, you're going to substitute in your X, Y, and Z values in terms of our T1 through T4s here into our original equation here. And what you're going to come up with after the substitution and the simplification here, you're going to come up with some formula. You're going to come up with the new formula here for your quadratic formula where you straighten it out and see what we'll go and look at that. So we're going to have, and there's going to be some cross terms in here. There's going to be a few cross terms that we're going to have. Let's go look at it up over here. A little easier to look at it. Okay, so this is what we ended up with after our substitution. And really what you're going to do, you're going to, by looking at your eigenvalues here, you're really eliminating the small amounts in this new formula that we have here. And you can see what's going on here. We start out, well, we got that minus 294, but then we have plus 147 T2 squared here. And let's look at that. That really matches our new equation that we have here, 147x squared here. And then let's look at the other one here. We got this 98 plus 98 times T3 squared here, which is really into our new quadratic, or in our ellipsoid, our new formula here, 98 times y squared. And then we have this 49 times t4, which is really 49 times z squared. So we got our x, y, and z coordinates here. But what we do here is if they're a very small amount, in this case they are, you can see here we've got some cross products here. So 0.07 here times t1 times t3. Then we have a 0.04 here times t2 and t4. And then what do we have? A 0.56 at T3 and T4 here. So we didn't totally eliminate our cross functions here when we made our substitution. But by coming up with our eigenvalues here, you can see our eigenvalues here, 147. Well, we got that minus 294. You're really not an eigenvalue because it's sitting on 0, 0, 0 point here. But nonetheless, you can look at the x squared here is 147. The y squared here is 98 as coefficients, and your z squared here is 49 as a coefficient. So you can see your eigenvalues that we calculated now match our new formula here. And we just eliminated those cross terms here because they're really a very small amount. So you no longer have any cross terms, and your eigenvalues that we calculated actually match our new quadratic equation here. X squared, y squared, z squared, no cross terms. Okay, so just looking at a pictorial here, we looked at our axis of rotation. So we were sitting here, sort of skewed off here with the axis. Now everything here is symmetrical, but it includes extra amount of information that's really not important to us when we're looking at the eigenvectors or eigenvalues. And we're not going to get into that discussion, but this is how it works here. So you can see it's skewed off here. But what we did do here, we straightened everything out. Just looking at it here, x, y, and z axis, you can see it right here. Here's our formula, 147 x squared, 98 y squared here, and then z squared 49 here. Showing it here, x, y, and z here. So we were sitting here with a skewed form here, or a pictorial here of our ellipsoid that was skewed off here. Our axes are really just symmetrical here to the skewed form, but we transformed it into this because that is what our eigenvalues are. Okay, so if we go down here and look at it just a little further here, I made some pictures here. The axis is before here, I'm showing in solid with the blue, red, and green. I can't rotate them all around here, but you can see as our rotation was made here, the rotation is showing with these red and green and blue dots or spheres here. Here's our center here, but there it is. So you can see there was a rotation that was made here. And if we go back and look at it here, here is this is before the rotation, my eigenplane here with the eigenvectors here. And then after the rotation, with our new formula, it would actually rotate this right up along our new axis that I'm showing here with these little spheres here, x, y, and z. Okay. All right. So then if we move over here, one other thing just to understand our rotation here, we talked about moving those x, y, and z vectors here, the green and our red and our blue vectors. You can see the plane here. So we started out with our blue and red here with this plane, and then we had this green vector here. And then what we've done here after this rotation, actually, it's just moved everything up here. The green one moves over here, blue moves up, red moves up by the degrees that we rotated here for this example. So eigenvectors control the direction here. And what's happened by doing that here, we actually have changed the value of our eigenvectors. And what they become is this here. Remember we had all those decimal points here for those different eigenvectors here. Now by doing the rotation here, by eliminating those cross terms here, we now have our eigenvectors for x, y, and z, and they're just sitting on a diagonal here. They're all of a unit of 1 right across here. Let's say is x, y, and z. So they're all of a unit of 1. We no longer are working with decimal points and fractions here of eigenvectors. They just turn into a unit of 1, and that's supposed to help us here when we're making our understanding of what's going on here. Okay, eigenvectors now all equal 1, x, y, and z terms here. All right, so let's just look up here. If we go to our eigenvalues here, same thing happens. The eigenvalues are just the magnitude that we're looking at. We're not getting into remember those eigenvalues we had here? All right, so they're just the magnitude, but they also rotate. Their direction is going to change along with the eigenvectors here, their rotation. Whatever rotated here in degrees rotated, I'm just showing x 73 degrees, y 64, and z 31. Same thing happens here with the eigenvalues. They rotate up. The eigenvectors control the direction. The eigenvalues are just the magnitude here. So you can see they all rotated up. I'm just showing them here, just so you understand what's going on here. Okay, the yellow ones are sitting on our plane. They rotate up along with our red one. They all rotate to match our eigenvectors here. And just to make a point here, when we are eigenvalues here, remember we got that 147, 98, 49 here for x, y, and z coordinates, and then we have that minus 294 here. The eigenvectors, our multiple here now for these eigenvalues is all 1 here. Before they would be a decimal point, as you'd be working with a group of eigenvectors. I'm just showing it here all as 1. That they all become a unit of 1, like 1, 0, 0, 0, and so forth here. Okay, so that's pretty much what's going on when we're talking about this axis rotation and really coming up with the eigenvalues here and eigenvectors of, in this case, of this quadratic ellipsoid that we're looking at, or this quadratic function. Okay, so that'll end our discussion.